Hello. So up till now we have studied about the heat conduction and various forms of Fourier law for one-dimensional and three-dimensional. And we have also studied about steady state and steady state heat transfer basics. So we will now study about internal heat generation. Then we will move on to generalized thermal energy balance, which is nothing but the first law of thermodynamics. So internal heat generation is the conversion of any other form of thermal energy like electrical, chemical, metabolic. Metabolic generation comes in chemical energy only, and mechanical into thermal energy. Like in our body, heat is generated due to chemical reactions. So this is the concept of internal heat generation. And one more thing, that the bigger the size of the body, the higher the heat generation inside the body. So since it is dependent on the size of the body, so it is a volumetric phenomenon. In practical cases, this internal heat generation is dependent upon the position where we are interested in. So in practical cases, internal heat generation is a non-uniform phenomenon and it is volumetric. But to simplify the subject, we are assuming that internal heat generation is uniform inside the body. The example of internal heat generation I have given here is like there is a wire represented by the blue rectangle, and potential V1 and V2 are applied across the two ends of the wire, and current I is flowing through it. A is the cross-sectional area of the wire, R is its electrical resistance, sigma is its electrical conductivity, and rho is not its density, it is resistivity, electrical resistivity. So from Joule's law of heating, that because of flowing of current through the wire, we can find the heat generation inside the body as I square times R or delta V times I. So if we want to find the volumetric rate of heat generation, is in watt per meter cube, whereas Q generation is in watt. So we can find this by dividing the Q gen by the volume of the wire. So I square R divided by cross-section area of the wire into length of the wire. So this was the concept of internal heat generation. We will use that concept in the later stages of this course. So next we should know about to derive any heat conduction equation is the generalized rate of thermal energy balance. So consider a system in which some energy is coming in, some energy is going out, and some energy is generating in the system, and system also have its property, which is the internal energy, which represents the temperature. Temperature represents the internal energy of the body. So temperature, we know that temperature also represents the degree of molecular activity inside the body. So that is related to the internal energy of the body. So system have property of internal energy U. So when there is a transfer of heat or thermal energy into the system represented by the blue box, so we can write the energy balance as it Q dot in minus Q dot out plus Q generation will be responsible for the change of the energy of the system. Energy in general and specifically internal energy, as we are writing here that Q stored is del E by del T. So but in most of the thermal systems, total energy is represented by the internal energy plus macroscopic energies like kinetic and potential energy. So kinetic and potential energy changes are negligible in most of the thermal system. So E is approximately internal energy only, and internal energy we can write like for incompressible system like mc del T by del T. So that's how we can write that. generalized thermal energy balance that will be used in most of the cases here. This is nothing but the first law of thermodynamics. This is just an energy balance. So in steady state there will be no change of temperature with respect to time. Okay, so it means that this term will be knocked out, which is represented here. So it means W by del T will be 0 and Q stored will be 0. As I mentioned above, E is the total energy of the system. Total energy is sum of all the microscopic energies. Sum of all the microscopic energy is nothing but the internal energy of the system. Okay, and macroscopic energy is nothing but the kinetic and potential energy of the system. Like bus is moving, it has kinetic energy. That is the thing I am talking about. And in microscopic energies, particles or atoms may have some kinetic energy that is comes in the internal energy of the system. So internal energy can be further divided into thermal energy. Or thermal engineers, we are interested in that, and other energies like chemical, nuclear, rotational, vibrational motion of the molecule of the atoms, atomic level. Okay, so in nutshell we can write total energy as internal energy plus microscopic energies. This. But for most of the thermal system we can write like this. That's why we have taken this assumption here. So next there is one important property which is we should know is the thermal diffusivity of the system. Thermal diffusivity represents the ratio of the ability of the medium to conduct heat with respect to the ability of the medium to absorb heat. So it is the ratio of the ability of the medium to conduct. It means it will be a ratio of thermal conductivity, and storage means it will be a in denominator there will be a specific heat of the body. So specific heat is the property of the medium which decides the ability of it to store or absorb thermal energy. For example, here we can see that specific heat of iron is 0.45 and specific heat of water is 4.187. We can see that specific heat of water is almost 10 times the specific heat of iron. It means that water can absorb 10 times more energy as compared to the iron for same mass and same temperature difference. In other words, we can say that when iron changes temperature by 10 degrees Celsius, water will change its temperature only by 1 degree Celsius, because less heat will be required to change the temperature of the iron, because it has less specific heat. So thermal diffusivity plays significant role in case of unsteady heat conduction. It decides the ability of the material to respond to the thermal effects. The higher the value means faster will be the response of the thermal system. Okay. Now we will derive the generalized one-dimensional heat conduction equation. So consider this generalized body. Same, some heat is coming in as Q in as Qx. Some amount of heat is going out at Qx plus dx. This phase is at x. So obviously this phase will be at x plus dx. So, and it has some internal heat generation Qgen, and property of this medium is internal energy, which is represented by the U. Okay, and since it is one-dimensional conduction, so temperature will be function of x, and we are considering generalized case, so it will be a function of time also. So Q in will be Qx, Q out will be Qx plus dx, and Qgen will be volumetric value of heat generation times the volume, and MC is rho times volume into times specific heat of this body, and del T by del T. So to find the value of Qx plus dx, we can use the Taylor series expansion. Taylor series expansion and expanding only up to first order term, annihilating all the other terms and putting that Qx plus dx value in the equation 1. So we will get and substituting the Qx value by the Fourier law minus k ax del T by del x. So why we are not that why we are using partial derivative, because temperature is not only function of, it is also function of time. So also area can be variation, there can be variation of area with respect to x. So we are taking it out. So this is the general heat equation in one dimensional. First term here represent the diffusion. Second term represent the generation term, and the third term represent the storage term. Okay, and materially, if we relax some of the assumptions and say that if the material is homogeneous and isotropic, then thermoconductivity will not be dependent on any direction. So we can take thermoconductivity out of this derivative, and taking out the thermoconductivity and dividing the whole equation by k, we get this. We get this equation, and after that we know that k by rho c is nothing but the thermal diffusivity, and putting that here, so we get one dimensional heat conduction equation here. And for writing for 3D, we can similarly incorporate y terms and z term, y diffusion and z direction diffusion, and q gen, and this 1 by alpha will remain same. One by alpha will remain same. And for prismatic body, where there is no change of area with respect to direction, so we can take the area also out, and if we take the area out, then it will be cancelled from this, simply like this. So we will get del square T by del x square, del square T by del y square, del square T by del x del z square. So this is nothing but the Laplace, and q gen by k is equal to 1 by alpha del T by del T. So the first term again represent the heat diffusion term, generation term, and the unsteady term. So this particular equation in 3-dimensional with k constant and area also constant with respect to direction. So this equation is known as Fourier-Biot equation in general. And if we apply one more assumption like steady state, the transfer is there, then the right hand side part will go, and only we are left with diffusion term and generation term. And that particular equation is known as Poisson equation. And second, next if we think about no internal heat generation, but the term is steady, but the term is unsteady, so and k is constant, so only generation term will be knocked out, so diffusion term and unsteady term will remain there. So that particular equation is diffusion equation. And if we assume steady state and no internal heat generation, then both this term, steady state, this term will be 0, and for no internal heat generation, this term will be 0. So we are left with only Laplace term, which is the diffusion term. So this is, since we are left with only with Laplace equation, so it is Laplace equation of heat conduction. So in the next class we will look upon the heat equation in cylindrical and spherical coordinate system. Thank you.